Okay, we are going to start lesson 5.3 with a little review of polynomial functions and how to graph those and what parent functions look like. So our first parent function that we learned was y equals x squared. And you guys learned, I hope you remember how to do a t-chart. So there's x and y. And then if we started with 0 and we plug it in to our function, we get that y is 0. If we plug in 1, y is 1. If we plug in 2, y is 4, and so forth and so on. So I'm going to put these on our graph. So we have 0, 0, 1, 1, 2, 4, and 3, 9. So that parabola looks like that. And the other side looks pretty much the same. They're mirror images. We call this symmetric. So it looks like that. Okay. And the easiest way to do that for the very first time is to do a nice little t-chart. And then we kind of talked about how transformations affect where the actual parabola is located. But the one thing I want to touch on is the domain and range of these parabolas. So domain of parabolas is, of course, negative infinity to infinity, but the range has a stopping point because there is this minimum down here where the parabola doesn't go past that point. It has a minimum. The range, the y values, the smallest they can get is 0, but they do go to infinity. This is going to become important as we talk about what the graphs of radical functions look like. Now, the other one I want to talk about really quickly. Oh, and also we learned when we talked about polynomials that the larger this value gets, it's just the skinnier our graph gets, right? It just gets skinnier and skinnier and skinnier. So when we talked about polynomials and we talked about our x's having odd-powered exponents, when we do our t-chart, it looks a little different. I'm going to put 0 down here in the middle because it's important that we look at both sides of this. So when we plug in 0, we get 0. So it originates right here in the middle. When we plug in 1, we get 1 for y. But when we plug in -1, we get -1 for y. And then 2 and 8 and -2 becomes -8. So that it actually has this nice little S shape to it. Well, sideways S. 1, 2, 3, 4, 5, 6, 7, 8. So it kind of comes, flattens out, and goes up. Now I'm sketching this with a stylus, so just go with it here. Okay, but that the domain for this is negative infinity to infinity, and the range is also negative infinity to infinity. So there aren't any limits on what is happening with these. Now, as we go in to your first example here for 5.3, it kind of dives right in without actually talking about what those parent functions of radicals look like. So I actually want to kind of touch on that first. So I'm going to go to your notes page, and even though it says, let's talk about the domain and range of square root 3 of x, I want to first talk about the domain and range of the parent function f of x equals just square root of x. When you're talking about domain, you're talking about the smallest or the largest that x can be. And that is increasingly important as you think about these radical functions, because we know that once we get underneath the radicand, and if we have an even power up in the index, that if this is even and our radicand is negative, that we don't have a real solution to that equation. So everything under the radicand has to be non-negative or greater than or equal to 0. So when you're looking at your parent function for square root of x, it's not going to be, your domain has to be greater than or equal to 0. But it can go infinitely. So it can get as large as we want it, because we can take the square root of really large numbers. We just can't take the square root of negative numbers. And I want to point out that this is in fact a bracket around that 0. So now when I make my t-chart for this, it makes sense we're going to start at 0 because that's our minimum, and the square root of 0 is 0. The next number we want to pick is the next perfect cube, which is 1, because 1 cubed is 1. And then 2 cubed is 8. Oh, except for we're doing square root here. Let me just confuse you guys. I'm very good at that. The square, 2 squared is 4. So that the square root of 4 is 2. And then our next perfect square is, of course, 9, which is 3. And if you think about, we're going to go one more. I got 16 and 4. So if I put this on my chart here, what you should notice is that it kind of looks like a half a parabola on its side. And that is what it's supposed to look like. So what we're doing with these radical equations is we're taking those parent functions of the polynomials and kind of turning them on their sides, and then looking at where the domain and range is limited. So now if we go to our function here, and I'm going to change over into green, and we've got that square root of 3x right there. What we can do is we want to pick numbers for our x that are, again, going to give us nice, perfect squares for our y's, so that our y's are whole numbers and not really weird fractions. But it gets a little bit tricky. So what we're actually going to do is we're going to pick our y's first in this case, because it's so much easier to pick y's when you kind of know what you need to get out of it. But I'm actually going to back up. I also want to make, well, is it going to let me? There we go. Sorry. I'm going to start with 0, because that's just a given, 0, 0. But what x do I want to look at next that's going to give me a y that's really pretty? And I need my y's, I'm going to use this number out front, to be multiples of that 3 that's there. So if you think about squares, we've got that 3 underneath. Well, our next 3 is, this will give us a perfect square, right? So if I plug in 3 for x, I'm going to get 3 times 3, which is 9. Square root of 9 is 3 out of my equation. Then if I think, okay, I've got to get another square, I'm going to multiply it by 3 times 3, which is 9. So that this number is 27, and my outcome is 9. So we're going to hold on to that and pull it up in our next recording.